Hi everyone, in this video we are going to talk about a nuclear reaction. I'm so excited because I love the nuclear energy. So here's the situation. Up until this point we've only been talking about chemical reactions. So we know that for these reactions we always conserve mass and matter. So what that means though is if we start with a carbon atom, you always end with a carbon atom. So that is for a chemical reaction. Now a nuclear reaction is something entirely different. For a nuclear reaction you could start with a carbon atom and end up with a palladium atom. Or you could start up with uranium and end with barium and krypton. It is so weird, but awesome at the same time. And so I hopefully, you can see the difference between nuclear and chemical, and then you'll be able to see why nuclear reactions are so vital and so amazing to be used as an alternative source of fuel. So let's back up a little bit before I get too excited and talk about some brief history. We need to come back. So in 1938, in Germany, we had two brilliant scientists named Hahn and Strassmann. And so what they did was a really neat experiment. They took uranium, which has 92 protons, and then it has a mass number of 235, and then they treated it with one neutron. So basically you had uranium here, and they shot all these neutrons at uranium. And what they saw was something so mind-boggling that they actually had to consult somebody else named Lise Meitner, a woman, to say, please help us, we don't understand what's happening, because they got such bizarre results. Instead of starting with uranium and ending with uranium, they actually were able to deduce or actually figure out that they were able to make barium, which was so bizarre. So barium has 56 protons, significantly less than uranium, and it has a mass number of 141. Now they also detected some krypton. So krypton has 36 protons and a mass number of 92. Now to fully balance this equation, we will know, and I don't expect you to know this yet, but you also have to add 3 neutrons. So now up until this point, I do not expect that you'd be able to create this. I don't expect that you'd be able to create the products. I don't think that you'd be able to balance it, but I do expect for you to memorize this. This is a super important equation, and you might as well get it down now, because this is where it all started. These brilliant scientists hit uranium with a neutron, and then all of a sudden uranium was just gone. It just disappeared, which was unprecedented. You have to imagine being in their position and seeing this and being like, where is the uranium? It can't just up and walk away. Well, actually it did. It went through a nuclear reaction, and now uranium is gone. So what's up with that, right? Let's look at the differences here between a chemical and nuclear reaction. So for a chemical reaction, we have been studying so far either an endo or an exothermic reaction. So endothermic meaning that we have to provide energy in order for us to transition from our reactants to our products. Now an exothermic reaction would be the exact opposite of that. It easily transitions from reactants to products, releasing energy. So now for an exothermic reaction, on average, so we're just going to kind of pick on average very globally, we would say a chemical reaction releases about 500 kilojoules of energy per mole of fuel source burned. Now we know for a chemical reaction that we always conserve mass, okay? We're never going to create mass, we're never going to lose mass, it's just not going to happen. Now, something very different happens for a nuclear reaction. So instead of releasing 500 kilojoules per mole for a chemical reaction, in a nuclear reaction we actually release 10 billion kilojoules per mole. 10 billion kilojoules per 1 mole of fuel. It is insane how much energy is released from a nuclear reaction. Now clearly, I have a lot of energy, so I can relate with a nuclear reaction. I love this stuff. It is so cool. But here's the reason. The only way you're actually able to do this and release that much energy is because we do not conserve mass and matter here. We don't. So actually what happens is that our mass of our reactants is slightly larger than our mass of products, okay? Slightly larger is all I expect you to know. You don't need to know the nitty-gritty of this. Now, this situation right here, where our mass of reactants is greater than our mass of products, is called our mass defect. So now this situation is so vital. This change in mass, or this loss of mass, is what is able to release 10 billion kilojoules of energy per mole of fuel source. And so this is what Einstein knew 30 years before Hahn and Strassmann even started doing this experiment. And so what Einstein did is he put together his equation, which hopefully we all know, which is your theory of relativity. So we have E is equal to mc squared. Now you've seen all of these letters before, but just not in this connotation, so let's map it out. E is energy, we know that. Usually it's in a unit of joules. M is mass. Usually it's in a unit of kilojoules, and that's dictated, kilograms, and that's dictated by the joule energy. Now, C is your speed of light. That is a constant that is not going to change. And at this point in this semester, I 100% expect for you to know what the speed of light is. So, what is the speed of light? I'm looking for an actual number here, the constant. What is the speed of light? And please give it to me in units of meters per second. Go. All right, did you get an answer? Hopefully you did, because we talked about this a lot when we went over electromagnetic radiation, but if you've happened to forget it, that's okay, it's been a while. So, speed of light is c, that's the constant, and it's equal to 3.0 times 10 to the 8th meters per second. You should get this down. However, I will always give you constants, but it's one of those that if you know it, it's just going to make life easier for you. I would also be very familiar with the theory of relativity, so we know that E is equal to mc squared. Okay? All right, so now, why are we talking about this? Well, we need to talk about something that is awesome, which is fission. So now, nuclear fission is basically when you take a very large molecule, but I don't like using that word molecule here for this, so we're just going to say atom, but realistically, we should probably say nucleus. So what happens is what happens for fission is when you break a large, we're just going to say atom, or nucleus, into smaller atoms or nuclei, okay? So it's very simple. You take a large atom, you break it apart into smaller atoms. But there's one component of here that you absolutely have to write down, and that it releases energy. If it did not release energy, we would not be studying it. So because it releases all this energy when we have this mass effect, it is so important and so cool, which is why we're studying it, and possibly why we'll be using it as an alternative source of energy. All right, so now, when will fission occur? When will fission or nuclear fission occur? Okay, 3 different times. The first one, which is probably the easiest one to determine, is by size, okay? So atoms with an atomic number, so an atomic number greater than 26. So if you have an atom that has an atomic number greater than 26, so it has more than 26 protons, it is likely to undergo fission rather than fusion. So now 26 is actually iron, and we'll come back to why that is in a little bit and what's so important or special about iron, but just kind of keep that in the back of your mind. There's something magical and beautiful about the atomic number 26 and iron, okay? All right, now number 2, and this part is really neat, and it has to do with the proton-neutron ratio. So your proton-neutron ratio. So now for something to have fission occur, or for a specific nucleus to undergo fission, usually what we want to have is an ideal ratio of 1 to 1.15. Now, just so we're very clear, that is your proton to neutron ratio. If you are at this ideal ratio, you're probably going to be stable. If you get greater than that, if you have more neutrons, then you're definitely going to undergo fission, all right? And again, we're going to come back to this, and I'll show you all the graphs and really neat stuff why, but I just want you to start getting these properties and these trends back in your mind and kind of solidify them here, so that when we see these graphs, you're going to be like, oh, I totally understand, okay? All right, so the last thing has to do with the energy of your incident neutrons. So now let's say you have an atom that has a number or an atomic number that's lower than 26. Well, realistically, it's unlikely to undergo fission. However, if you hit that atom with really high energy neutrons, it is likely that that atom will actually undergo nuclear fission, okay? So there's a lot of different properties that we can go through here, but there's 3 main ones that I want you to know. So if your size, if you have an atomic number greater than 26, If you have a proton to neutron ratio that is different from 1 to 1.5, especially if you have more neutrons, okay, more neutrons there, definitely going to undergo nuclear fission. And then last one is if you happen to hit that atom with very, very high energy neutrons, then something crazy is obviously going to occur. Now, let's end here with one quick question to just make sure you understand. So here is the question. Which element is more likely to decay? Okay, so decay, just getting smaller, essentially decompose, not really, but you can think of it that way until we give you a better definition. So decay by nuclear fission. And I'm going to give you just two options here. So it's either going to be carbon or Pu. Go. All right, did you get an answer? Hopefully you did, because all you had to do was look at those three lists that we gave you earlier and just come up with an answer. And so hopefully what you did is looked at carbon and said, okay, I know carbon has an atomic number of 6. If you don't know that off the top of your head, you can just look at the periodic table. And same thing with plutonium. So you could look at plutonium and say, all right, this one has an atomic number of 94. Are either of these with an atomic number greater than 26? Yes, plutonium definitely is. Plutonium is much, much, much more likely to decay by nuclear fission than carbon. All right, that's all I've got for you today. Have a great week. Take care of yourself. Drink water.